They're everywhere, these invisible forces.
Exactly. And today we're going to dive into one that's, well, incredibly powerful and totally fundamental, the strong nuclear force. It's working away deep inside matter, mostly unseen.
Right. And this deep dive is all about exploring that force. It's basically the reason matter, sticks together and exists stably. Without it, the universe would be, well, not much, really. Very different.
To help us kind of get our heads around it, we've got some really great source material. Stuff that breaks down the strong force, its unique features, and why it's just so critical.
Our mission, if you like, is to understand how this force, acting at these unbelievably tiny scales.
Like unimaginably small.
Yeah, impossibly small scales.
Yeah.
Is responsible for the structure and stability of pretty much everything we can actually see and touch.
Okay, so where do we start? The beginning of figuring this out.
Let's rewind a bit. Back to the early 20th century. We just discovered the atomic nucleus, thanks to Rutherford.
Ah, okay, the tiny, dense core of the atom. And it's packed with protons, which are positively charged.
Exactly. And right away, there's a puzzle. Basic physics tells us, like, charges repel. Positive repels positive.
Right, like trying to push two north poles of magnets together. They just, nope. So the nucleus should fly apart, shouldn't it? All those protons pushing each other away. It seems like it should just explode. A real atomic head-scratcher.
Precisely. And it got even more puzzling when we looked at heavier atoms.
Because they have more protons jammed in there.
Even more protons, meaning even stronger electrical repulsion. Yet elements like gold or lead are perfectly stable.
So that screamed there must be another force, something much stronger pulling things together inside that nucleus.
Something attractive, yeah.
Yeah.
Something that could easily overpower that electromagnetic push.
Then Chadwick discovers the neutron. Did that solve it? Added some neutral bulk in there.
It helped paint a fuller picture of the nucleus, adding mass without adding charge. But no, it didn't fundamentally explain the stability. It reduced the repulsion density a bit, maybe, but didn't provide the glue.
So there was still this missing piece, the super strong sticking power.
And that missing piece, we now know, is the strong nuclear force. And the key thing is its range.
Right, it only works over incredibly short distances.
Incredibly short. We're talking about 10 to the minus 15 meters, a femtometer. That's like the size scale of the nucleus itself, or even smaller.
Wow, tiny.
Within that tiny range, it's overwhelmingly powerful. Way, way stronger than the electromagnetic repulsion between protons. It clamps them together.
Okay, so it dominates in its little neighborhood, but its influence drops off super fast outside that.
Absolutely vital that it does. Critically important. If the strong force had a long range, like gravity or electromagnetism,
Well, think about it.
you would just start pulling everything together.
Oh,
Like
wow.
all nuclei attracting all other nuclei across space. Potentially, yes. It could theoretically collapse all matter into one giant something. Its short-range nature is essential for having distinct atoms, molecules, planets, stars, everything.
Okay, got it. Super strong, but only up close. So how does it work? What's the mechanism? This is Yukawa time, isn't it?
Exactly. Hideki Yukawa, 1935. He had this brilliant, kind of revolutionary idea about how forces work at a quantum level.
Not just action at a distance, but something being exchanged.
Precisely. He proposed that forces are mediated, carried by particles being exchanged. And for the strong force holding protons and neutrons, nucleons, we call them together, he predicted a brand new particle, a type of meson, specifically the pi meson, or pion for short.
Pions. So these are little messenger particles constantly bouncing between the protons and neutrons.
That's a pretty good analogy, yeah. They're constantly being exchanged, and this exchange creates the attractive force binding the nucleus.
Okay. And the properties of this pion explain something important, right?
Yes, its mass. Yukawa predicted its mass, and it turned out to be about 200 times heavier than an electron. Now, there's a principle in quantum physics.
Oh.
Haha, no, it's elegant. It links the mass of the force-carrying particle to the range of the force. Heavier particle, shorter range.
Ah, so the pion being relatively heavy perfectly explained why the strong force only worked over those tiny nuclear distances.
Exactly. It fit beautifully. Theory predicts a particle with a certain mass to explain the force's range, and then Moll.
They find it. When was that?
Experimentally confirmed in 1947. It was a huge validation of Yukawa's idea. He got the Nobel Prize for it, deservedly so.
Brilliant. So problem solved. Pions hold the nucleus together.
Well, yes and no. It was a massive step. But it turned out that this pion exchange picture describes what we now call the residual strong force.
The residual, okay, like leftover, so there's a deeper level.
There is. The story gets even more fundamental. To really understand the strong force, we need to look inside the protons and neutrons themselves.
Because they're not fundamental particles either.
Turned out they weren't. Through the 50s and 60s, particle accelerators started finding loads of new particles, a whole particle zoo. Too many to all be fundamental. It hinted that protons and neutrons had inner structure.
Right, the Hadron Zoo. Must have been wild trying to make sense of all those new discoveries.
Exciting and confusing, yes. Then, in 1964, Murray Gell-Mann and George Zweig independently came up with the quark model.
Ah, quarks. This is where it gets really interesting.
Yes, they proposed that particles like protons and neutrons called baryons are made of three smaller things, quarks. And mesons, like our friend the pion, are made of one quark and one antiquark.
So the force we just talked about, the pion exchange between protons and neutrons, is actually a side effect of something even more basic happening inside them.
Exactly. The fundamental strong force operates between these quarks, gluing them together to form protons and neutrons. The force between the protons and neutrons is just a residual effect leaking out, mediated by those quark-antiquark pairs, pions.
Okay, wow. So what's the theory for that fundamental force?
That theory is called quantum chromodynamics, or QCD, developed in the early 1970s.
Quantum chromodynamics. Chromo like color.
Precisely. It introduces a new kind of charge, analogous to electric charge, but called color charge. Nothing to do with visible color, of course.
Just a name for a quantum property.
Right. Instead of just positive and negative like electric charge, color charge comes in three types, whimsically named red, green, and blue, plus three corresponding anti-colors, anti-red, anti-green, anti-blue.
Okay, red, green, blue, like primary colors of light almost. And quarks have these color charges.
Yes. Each quark carries one of the three color charges, and antiquarks carry anticolor.
And the force carriers, like the photon for electromagnetism.
For the strong force, the carriers are called gluons.
Gluons, like glue.
Exactly. They glue the quarks together. There are 8 different types of gluons. And here's a crucial, really weird difference from photons.
Okay.
Photons carry the electromagnetic force, but they don't have electric charge themselves. Gluons, however, do carry color charge.
Wait, the force carriers themselves have the charge they mediate? The glue is sticky to itself.
You got it. Gluons interact with quarks, but they also interact strongly with each other. This self-interaction is what makes QCD mathematically, well, very challenging, much more complex than electromagnetism.
I can imagine. Sticky glue interacting with itself sounds like a recipe for complexity.
It is. And it leads directly to some of the strong force's most distinctive and frankly bizarre properties.
Okay, let's get into those properties. We know it's strong, we know it's short range. What else makes it so unique?
Well, strength first.
Yeah.
Yes. Within its tiny domain, it's by far the strongest force we know. Hands down champion.
Right. Strongest of the 4 fundamental forces inside that femtometer box.
Exactly. Then there's this property called confinement.
Confinement. That's the one that says quarks are never found alone, right? They're always locked up inside particles like protons or neutrons.
That's it. You can't isolate a single quark. And the reason is fascinating. Unlike gravity or electromagnetism, where the force gets weaker as you pull things apart, the strong force between quarks doesn't get weaker with distance. It stays roughly constant, or maybe even increases slightly.
Seriously. So the further you try to pull 2 quarks apart, the harder the force pulls them back, like an unbreakable rubber band.
Kind of like an infinitely strong rubber band, yes. It's completely counterintuitive based on everyday forces.
So what happens if you just keep pouring energy in trying to break that band?
The energy you put in builds up in the field between the quarks. Eventually, you put in so much energy that it becomes energetically cheaper for the universe to just pop a new quark-antiquark pair out of the vacuum using Einstein's EMC atom.
Wow.
Yeah. So the original quark you were pulling grabs the new antiquark, and the original antiquark grabs the new quark, and instead of getting free quarks, you just end up creating 2 new particles, hadrons. You can't win.
That's amazing. It's like trying to snatch a bar magnet. You just get 2 smaller magnets, each still having a north and south pole. You can never isolate a single pole.
That's an excellent analogy. And this leads to why hadrons are always color neutral or colorless.
How does that work with the red, green, blue charges?
In baryons, like protons, 3 quarks, you always have 1 red, 1 green, and 1 blue quark.
Right.
Like mixing primary colors of light. They combine to make white or neutral in terms of color charge.
Okay. Red plus green plus blue, white neutral.
And in mesons, quark-antiquark, You have, say, a red quark and an anti-red antiquark. Again, the color and anti-color cancel out, resulting in neutrality. Nature insists on this color balance in observable particles.
Fascinating. Okay, so confinement is weird. What else? You mentioned something paradoxical earlier.
Ah, yes. Asymptotic freedom.
Right. Freedom sounds like the opposite of confinement. How can the strong force be both confining and allow freedom?
It sounds completely contradictory, doesn't it?
Yeah.
But it's a cornerstone of QCD, experimentally verified. It means that while the force is incredibly strong at typical distances within a proton, if you probe quarks at very, very short distances.
Just really smacking them together hard in an accelerator. High energy.
Exactly. Very high energies correspond to very short distances in quantum mechanics. Under those conditions, the strong force between quarks becomes surprisingly weak.
Weaker, not stronger.
Much weaker. They behave almost like free particles, hardly interacting with each other when they're extremely close together.
So the unbreakable rubber band goes totally slack if you push the ends right next to each other. That's wild.
It is wild. It's due to the complex interplay of the gluons. Those gluon self-interactions, which make the force strong at long distances, actually cause an anti-screening effect that weakens the effective color charge when quarks get very close.
Anti-screening. Okay, that's deep. But this asymptotic freedom, it must have been crucial for figuring things out.
Absolutely monumental. It was predicted theoretically in the early 70s by Gross, Wilczek, and Pulitzer. They won the Nobel Prize for it in 2004.
Because it explained experimental results.
Precisely. Experiments smashing protons together at high energies were seeing evidence that the quarks inside were acting almost freely, which seemed bizarre until asymptotic freedom explained why. It was powerful proof for quarks and QCD.
So let me recap the weirdness. Super strong up close, confined, can't pull quarks apart, yet paradoxically weak at extremely close distances. All because of color charge and those self-interacting gluons?
You've nailed the key properties. Strength, short range, confinement, and asymptotic freedom. They all emerge from QCD.
Okay, so we've dived deep into the force itself. Now let's pull back again. Why does all this weirdness at the femtoscale matter for, us, the big picture?
Well, it matters fundamentally. Think about it. Without the strong force overcoming proton repulsion.
No nuclei beyond hydrogen.
Exactly. Protons would just repel each other. The universe would be almost entirely hydrogen. Maybe a little helium from the Big Bang, but that's it.
Wow. So no carbon, no oxygen, no iron, none of the elements that make up planets or life.
None of them. Forget stars doing complex fusion. Stars fuse hydrogen into helium, sure, but to build heavier elements like carbon, oxygen, silicon, iron, you need nuclei to stick together. You need the strong force.
So the strong force is basically responsible for the entire periodic table beyond hydrogen and helium. It's why stars can be element factories.
That's absolutely right. It enables nucleosynthesis in stars, creating the building blocks for everything solid and complex in the universe, including us.
That's profound. It's not just holding my atoms together right now. It's the reason the atoms themselves could even form in stars billions of years ago.
Precisely. It underpins the structure of almost all visible matter. And remember, the force between protons and neutrons, the nuclear binding we started with, is just that residual effect of the fundamental quark-gluon interactions happening inside.
Incredible. A tiny force with truly cosmic consequences.
It really is. And, we've learned a massive amount, but the story isn't completely finished. QCD is hard.
Still challenges. What are physicists still trying to figure out?
Well, calculating things from first principles in QCD is extremely difficult because of those gluon self-interactions. For example, predicting the exact mass of a proton just from the quark masses in QCD equations requires immense computing power simulations called lattice QCD.
So theory is clear, but the math is just really, really hard.
Very hard. And fully understanding the mechanism of confinement isn't trivial either. Plus, exploring matter under extreme conditions like the quark-gluon plasma, a state where quarks and gluons are deconfined, which might exist inside neutron stars or existed just after the Big Bang, that's a huge area of ongoing research.
Quark-gluon plasma, like a soup of quarks and gluons before they condensed into protons and neutrons?
Sort of, yeah. Creating and studying tiny droplets of it in particle colliders is a major focus, so lots still to learn.
Even about the strongest force, there are still mysteries.
Absolutely, which makes it exciting.
Okay, so let's try and wrap our heads around this journey. We started with a puzzle. Why doesn't the nucleus fly apart? The answer: the strong force.
Right, initially explained by pion exchange, the residual force.
Then we went deeper, inside protons and neutrons, to find quarks and the fundamental strong force described by QCD, with its color charge and gluons.
And its weird properties. Confinement, locking quarks up.
And asymptotic freedom, letting them act freely when super close.
And the payoff.
Yeah.
This force makes nuclei stable, allows stars to forge heavy elements, and ultimately makes planets and life possible.
It really is the bedrock of structure in the universe.
Couldn't have said it better. Silent, unseen, but utterly essential.
It leaves you wondering, doesn't it? This force, operating on scales we can barely conceive of, dictates so much about the cosmos. What else might be lurking down there? What other hidden rules are shaping reality in ways we haven't grasped yet?
It's a humbling thought. The connection between the incredibly small and the vastly large is always full of surprises, always more to discover.